Well, thank you very much for the introduction, and thanks the organizer for organizing this wonderful conference. As the title suggests, I will be talking about the Einstein equation. So let me say a few words before going on with the slides. So, of course, by now I think people are already familiar with the Einstein equations. I will be talking only about the Einstein vacuum equations, in which case you are talking about a four-manifold with a Lorentzian metric G and verifying Ricci of G equal to 0. So this is the shortest equation you can possibly write. And yeah, you can even take away the G. Anyway, so and obviously we have to solve this equation. In the sense, you have to find metrics which verifies the equation. Now, the first thing to be said about it, and of course people already know, even those who are not familiar with general relativity, that these are hyperbolic equations. So they're hyperbolic because of the metric being Lorentzian, and therefore it leads to an initial value problem. So there is an initial value problem formulation in which you start with a three-manifold, a metric, a Riemannian metric given on sigma 3, and a tensor, a symmetric 2 tensor, K bar. And these are like, in the case of, you always have to compare with, say, the wave equation, the standard wave equation, where you prescribe phi and the time derivative of phi. So this is prescribing G and K, which will be, once you construct the spacetime, this will be essentially the time derivative of the metric. Okay, so that's so this is the initial value. Of course, you have some constraint equations here which have to be solved. That's a minor detail, though lots of people work on just the constraint equation, and there are lots of interesting results. But we are really interested in the evolution problem, right? So assume that you have initial conditions and you want to solve. Now, also another thing that I should say. General relativity is split into problems which are cosmological problems and problems which correspond to isolated physical systems. So I'll talk about the latter. In other words, I assume asymptotic flatness. Now, so what that means is that you are looking for metrics which look Minkowskian at infinity, or in terms of the initial data, that means that this metric looks like the Euclidean metric at infinity, and the second fundamental form looks like 0. And of course, you have precise ways of formulating this, but roughly that's what it is. Anyway, so this is asymptotic flatness, but then obviously we are interested in solving this problem. So there is a local existence result, which we all know. It's due to Yvon Choquet-Brouat, 1952, which tells you that at least you can construct, given specific initial data with some level of differentiability, of course, as usual, you can construct a solution up to a certain time. And then there is also a maximum time of existence, which is called the maximal global hyperbolic development, right? So this is a sort of the maximum possible extension that you can make by local existence arguments. Anyway, so keep in mind that that's the maximal global hyperbolic development of the spacetime. And obviously, all of general relativity, all of mathematical general relativity is about giving information, providing information about this maximal global hyperbolic development, right? All right. So now, the next thing that you do whenever you have a very difficult nonlinear problem, you look for stationary states, right? So stationary states. So these are states which in some sense are independent of time. Now, of course, time in general relativity is a more complicated notion, but still you can make sense of it. So it's actually relatively simple. You say that the spacetime is stationary if there exists a vector field T, which is which is time-like at space-like infinity. In other words, if you have a light cone at every point, then as you go towards infinity, the vector field is more and more like the standard d over dt in Minkowski space, right? Okay, so that's so a stationary state means there exists such a vector field such that the derivative of the metric with respect to t is equal to 0, right? So that's how you define stationarity. It's not too difficult. And then, of course, there are examples. So there is the next thing that we know is that there is this incredible family of solutions of the Einstein equations under this assumption and asymptotically flat assumption, which are the Kerr solutions, right? So this was a family. So this is, we are typically interested in absolute value of A strictly less than m. A is equal to 0 corresponds to Schwarzschild. A equal to 0, and of course Minkowski means A equal to 0 equal to m equal to 0. So both these parameters are equal to 0. All right, so these are the stationary states. And then, once you think that you know all the stationary states, which of course is a problem. So I'll mention here that there are 3 obvious problems connected with the Kerr solution, with the Kerr family. Then you can conjecture, as people have done, the so-called final state conjecture, right? State conjecture, which is that if you take any initial data, then asymptotic, well, it's going to be very complicated. The interactions are going to be very complicated. The nonlinear analysis is going to be incredibly difficult. But the hope is that eventually you are going to see, in any finite region of state, you are only going to see a Kerr solution, nothing else, right? So this is like the soliton resolution conjecture, if you want. But I'm interpreting this final state conjecture in the sense that essentially things are stable, because otherwise, right? I mean, from a physical point of view, it doesn't make any sense otherwise, right? So the
Can I ask a question?
Yes.
That doesn't allow merger of.
Yeah, it does allow merger also. So this will be part of the final state conjecture. There are all sorts of things. Initial data are very complicated. All sorts of things happen. Black holes emerge, right? Then they will coalesce, maybe some of them. Some others will go far away.
We need some food for LIGO.
Right. But I mean, the LIGO, I mean, whatever is done at LIGO is based essentially on this picture. I mean, so, the recent experiments are totally based on the assumption that this picture is correct. Okay. Now, in order for the picture to be correct, you have to do a lot of things, right? So first of all, the first thing, the simplest thing maybe that you could ask is, do this, is Kerr family, so the rigidity issue, rigidity, is this Kerr family rigid? In other words, are there any other stationary solutions besides those? So these are solutions that you can find explicitly. These are explicit solutions which are found in 62, 63 by Kerr and Schwarzschild even in 1915, very early on, right? All right, so so the rigidity conjecture tells you that there are no other stationary states, right? The second thing is stability, of course. Stability of the Kerr family. So in other words, if I make a small perturbation of the Kerr solution, the expectation is that you are not going to get something else, right? Because if you get something else, then it's clearly that the Kerr solutions have no physical reality. They exist in mathematical universe. They are beautiful. You can study them if you want, but they will have no physical significance, right? And of course, then this final state conjecture will be false. In fact, if any of these things that I'm writing now will be false, then the final state conjecture is also false. Anyway, so beyond stability, there is also collapse. The issue of collapse. I mean, can you actually form black holes at all? I mean, of course, we are told that they form when you have a collapse of a star, for example. You will form a black hole, but is it true? I mean, is this picture true? So that's another mathematical question for us. And then if you want to go, so these are 3 fundamental questions which are called I like to call them reality. So the tests of reality of the black holes, right? If these are false, then, bye-bye black holes from a physical point of view, right? Now, of course, beyond that, if you want to go to the final state conjecture, there are many, many other things involved. There are many, many steps. Like, for example, as you said, take now 2 black holes. This will be just one black hole. This is the one body problem. But of course, you have to study the 2 body problem and body problem. Then there are other issues that have to do with the cosmic censorship, which is another fundamental conjecture in general relativity, which says roughly that the only singularities you can have, by the way, singularities, besides stationary states, of course, singularities of nonlinear PDEs are also fundamental if we want to understand their evolution, right? Now, it so happens that singularities which are known in general relativity in this asymptotically flat regime are the ones of the Kerr family. So the Kerr family, or at least the Schwarzschild family, has a singularity in the black hole. So this is a remarkable thing about general relativity, that it splits. A black hole splits the space-time. It's something about the space-time. Splits the space-time between a region, which is the black hole region, and the outside region. And the outside region is smooth. Is regularity. The only singularities will occur in the black hole region. That's essentially what we believe. Cosmic censorship is a way of formulating that statement, that the only singularity you can have are in black holes. You can't have naked, so-called naked singularities.
But it's not true.
Of course not. I'm talking about here a program for the next 100 years, right? I mean, this may take even more than 100 years, right? But obviously, there are lots of steps, and there are lots of simplifications that you can make, and of course there is a lot of activity. You can simplify many of these problems. Anyway, the problems that I've been mostly interested in the recent years are these three, right? So, and I'm going to talk about this, the issue of stability in this talk. All right, so let me go to the slides. All right, so how does this go?
The button on the side.
This one?
No, the button, the round disc button on the side of it. The center button is laser, and the side buttons are the advanced.
Okay, very good. All right, so here is a Kerr family. Oops, what happened? Okay, very good. Now I have to be very careful what I do. Maybe I shouldn't even use this. It's better. All right. So you see, is it okay now? No, I'm still not fine. Ah, yeah, here in the center you say. Okay, very good. Now I understand. So I should never touch these buttons. All right, so here is a Kerr family expressed in so-called Boyer-Linkus coordinates, which are like polar coordinates. And you see the metric looks extremely explicit, even though it's a solution of a very complicated nonlinear problem. You don't have to remember these things. I just want to glance very fast over this formula. The important thing is that all the coefficients that you see here of the metric are independent of t, of the t variable, and that corresponds to the fact that you have stationarity. In other words, this vector field is a Kinney vector field, indeed, in the sense of this definition. And you also see that the metric is asymptotically flat also. You see that these coefficients are very explicit, and as r goes to infinity, you get the Minkowski space. In addition of stationarity, you also have Axilly symmetric. So the Kerr family, as you see, these coefficients are also independent of phi, which corresponds to the fact that the vector field z, which is d over d phi, is indeed a Kinney vector field. Now the Schwarzschild solution is the particular case when a equal to 0. The metric becomes much easier. You see you have this delta over r, but you see, of course, that you have some kind of strange singularities. Of course, these singularities occur here also, but in this case, it's very easy to see that when r is equal to 2m or r is equal to 0, this metric sort of becomes singular. Now, the singularity, the singularity at r equal to 2m is not a real singularity. It turns out that you can actually extend the solution, and in fact, r equal to 2m is just the boundary between the so-called black hole and the exterior region. Now, these are, you don't have to take, I mean, obviously, if you've never seen these kind of Penrose diagrams, you might be a bit confused. The important thing to look at is maybe, if you are not familiar with this picture, is to look at various values of r. So you see, the interesting values are r equal to 2m, which corresponds exactly to the boundary between the black hole and the exterior region of the spacetime. R less than 2m, this is the black hole region and maybe the white hole. The white hole is not very physical, so we will throw it out. We are not interested in it. There is a curvature singularity at r equal to 0. Here, the metric actually does become infinite. The curvature of the metric becomes infinite at r equal to 0. Again, I will not be, so this is the black hole by itself is, of course, a fascinating thing. That's where the singularities will occur. But I will be interested, when we talk about stability, we are interested in the external part of the black hole, all the way up to the horizon, right? So this is the part that I drew here. There are some other interesting numbers. R equals 3m corresponds to the existence of so-called trapped null geodesics, which are lead to lots of problems, both mathematical, but especially mathematically, I would say. And finally, there is R equal to infinity, which corresponds in this picture to these boundaries, right? So these boundaries are really at infinity, right? Now, the light here propagates at 45 degrees, right? So as you see that if you are inside, you cannot escape. You'll eventually hit the singularity. While of course, if you are outside, if you are unlucky and you go in this direction, you'll get into the black hole and you hit the singularity, but you can also escape, right? You can escape to infinity. So that's the difference between the external, very roughly, between the external and the black hole region. All right, so now, sorry, I'm not doing well here. Okay, so the Kerr spacetime is very similar, at least in the exterior region, except that the horizon now is at r equal r plus, which is the root of this polynomial. So again, it's very explicit. The black hole is slightly different in the sense that you don't have that singularity at r equal to 0, but I'm not going to get into this region. I'll be interested in just this, and as you see, the picture is very similar. This is a space-like hypersurface, which will play the role that I want to give initial data later on. I want to perturb the Kerr solution, and I want to give initial data on something like this. All right, so there are, again, the external region, r larger than r plus, event horizon, which is exactly the boundary, the black hole region, which is r less than r plus. Here is again the same picture. Well, this is the one that you should look at. That's external region. This is the event horizon where r was equal to r plus in Kerr. Now here you also see the vector field capital T, which is the stationary Koenig vector field. You see it's time-like. It means it goes in this direction as you approach infinity. So this is, remember, this is the boundary at infinity. While now the remarkable thing that happens is that T becomes actually space-like near the horizon. So even though it started by being time-like, near the horizon it's space-like, and that leads to lots of issues. I mean, it leads a lot of interesting physical issues, but also mathematically to lots of difficulties. Because if, for example, energy is always tied to a Koenig vector field, in particular time-like Koenig vector field. So coercivity is, of course, tied to the fact that T is time-like. In places where T will be space-like, coercivity will disappear, right? So you have, anyway, this is something that I just want to draw your attention at this point. All right, so this is now the conjecture of the stability conjecture. So stability of external Kerr. So in other words, I'm interested only in this region. I take this initial data. I take the initial data here exactly of the Kerr solution, right? So Kerr solution has, of course, associated initial data on any space-like hypersurface. I take that data and I perturb it a little bit, right? And the conjecture says that small perturbations of a given external Kerr solution have maximal future development, right? In other words, I develop solution as far as I can, which converge to another Kerr solution. So in particular, it will be complete in this direction, and it will look asymptotically, it will look like a Kerr solution, but maybe a different one. In other words, I can start with A and M, and the final states will be different from this. Okay? Which leads again to many other difficulties, as we know. I mean, whenever you have these kind of situations, you have to do careful analysis. All right, so what are the difficulties of the black hole stability problem? Well, the first one, which is common to any geometric problem, in particular general relativity, is a so-called gauge covariance. I mean, you write down the equations. Well, to write it like this, it's useless. You want to write it in some kind of coordinates, let's say. But then, as you pick coordinates, you maybe will get a system of nonlinear wave equation if you are careful. But it may be that instabilities in that system of coordinates will mean nothing else that you picked up the wrong coordinates, right? So you have to be very careful what you mean. You have to work as much as you can in an invariant fashion, which is not easy given the nature of this equation. So in any case, you can, this, of course, this issue of gauge covariance is connected with proper linearization. If you change variables, change variables in a nonlinear equation, the linear equations will look very different, right? So, well, okay, so then you can try to linearize at the level of metric coefficients in a given coordinate system. That's not a very good idea, as it turns out. You can use connection coefficients, or you can use curvature. So you can linearize at the level of the curvature. This is actually the way to go. And I'll explain maybe a little bit more later on. And then another problem, of course, is that these equations are quasi-linear, right? So in other words, the characteristics depend heavily on the solution itself. And the characteristics, of course, have to play a fundamental role in the story, right? Because this is where light the gravitational waves or light or whatever if you have matter fields, they will propagate along null characteristics. So there is a non-trivial null structure. I mean, we heard about the null condition. These equations can be viewed at some level as some system of nonlinear wave equations. So you expect the null condition to play an important role. However, if you try to use a null condition in the coordinates used by von Choquet-Brouat, which are called wave coordinates, it's not there. There is no null condition. There is a so-called weak null condition, but that's very different. Anyway, so to find the correct null condition is also a highly non-trivial issue. So to detect, in other words. And of course, this also has to do with the problem of coordinates and gauges. Now, even if you look at a linear problem in Kerr, in other words, you fix your background. So this is much simpler. You fix your background. This is sort of a baby linearization. You assume that you are in Kerr, and you look at some linear problem, like, for example, just the standard wave equation in Kerr. This is already a highly non-trivial problem, which was only understood due to, after 30 years maybe of 30 or 40 years of efforts, was only understood in the last 10 years by essentially by mathematicians, by introducing all sorts of new techniques which take into account the fact that Kerr has limited symmetry. So the vector fields, the standard vector fields are not enough. The vector fields which are tied to symmetries of Kerr. The fact that there is an ergo region in which you have issues even with the energy, and the fact that you have presence of trapped null geodesics, which is actually, it turns out to be technically the most difficult of all. So what are these trapped null geodesics? These are geodesics that don't escape either in the black hole or at infinity, and stay, in fact, in space-time at finite values of r. And as we know from geometric optics, they will create lots of problems, right? Okay. All right. So finally, but not least, you do expect, no matter what kind of linearization you do, to have some kind of linear instability connected with gauges. And this is due to the change in A and M, right? So the final, as I said, the final A and M will be different from the ones you perturb. And that has to sort of be read in some kind of instability of the linearized equations. And also the position of the final black hole also will change, right? So you have to take that into account also. That will also create instabilities. All right, so, okay. So now here is a little bit, bear with me with a little bit of technical stuff, but it's not very difficult. Let me say it here. So you see, typically when you have a space-time, the best way to analyze it is not using coordinates, but using frames, right? So why are frames important? So if frames are simply vector fields in space-time, which are null. So in other words, G is 3, is G 4, E4, equal to 0. And therefore, they correspond somehow to propagation, right? So that's why they are very, very important. In coordinates, it's very hard to write things like this, right? So that's why frames are very important. And then once you have, you also normalize this so that E3, E4 is equal to -2, right? And then once you have that, you can also look at the space-time perpendicular to these two, and you write down E1, E2, two other vector fields which are orthonormal relative to themselves, and of course perpendicular to this one, right? So that's what it's called a null frame, which plays a fundamental role in just about anything you want to do in GR nowadays, right? So okay, so the first thing to take into account is this null frame. Once you have the null frame, you can construct connection coefficients, right? Which simply means, which are typically denoted by gamma, which simply means that you take derivative of relative to the frame, let's say alpha, E beta, E gamma, right? So you take covariant derivative of the frame relative to the frame, and then you project it again in the direction of the frame. So this gives you the so-called gammas. And then next thing you do is you look at the curvature. So this is the curvature tensor. And you also decompose the curvature tensor, right? So the curvature tensor is a 4 tensor. You also decompose it relative to the frame, and you get various coefficients. For example, if you look at R, E4, E1 or E2, so let's call it A, capital A refers to E1 or E2, E4, EB, right? This is called, say, alpha AB. And it's certain components of the curvature. And what I wrote there are various combinations of different components of R relative to the null frame. And well, very often in general relativity, you will see these kind of notations, right? So anyway, so again, what you have to keep in mind, however, maybe I don't want to scare you with too many notations. What you should keep in mind is that the gammas verifies equations which related to curvature. So for example, this is a very important equation, E4 gamma times gamma is equal to curvature. Of course, I'm writing it in a symbolic manner. Here you should think about various components of gamma, and various components of curvature. So you'll have a lot of, you can fill a blackboard with many equations. Oh, sorry. Yeah, so you can fill the blackboard with various equations. And finally, the other equation, so there is another one relative to E3, so there is something similar. And then there is something similar about curvature. So there is E3 of R plus gamma times R are derivatives of curvature, but derivatives which will be different from the E3 derivative, which you put it here. And E4, so very roughly, right, times R is also. Of course, again, as I said, I mean, if you write down all the components here, you can fill up the blackboard. The important thing to realize is that these are the most fundamental of all, and these are, in fact, nothing else but Bianchi identities. And it's not too difficult to see in a first approximation that they are actually, well, first of all, they arrive from, I mean, they can be derived from the standard Bianchi identities, which are beta, gamma, delta, sigma, plus, right, you take cyclic permutations of these indices, right? So let me write it just like this, equal to 0. And the fact that you also have R alpha beta, you have this kind of divergence. So this is a divergence of gamma delta equal to 0. So this equation follows from this one. They are in fact equivalent if the Ricci of G is equal to 0. In other words, if we are in the dimensional vacuum equations, right? Anyway, so this is what I want to say is that you can view this as glorified Maxwell equations. And somehow, this is extremely important because it tells you that somehow the hyperbolic character of the equation is most explicit in terms of the curvature. So the curvature being also invariant Of course, this is obviously extremely important. Okay, so these are the hyperbolic. This is the hyperbolic character of the equation, and therefore the way to think about all this is that somehow you first estimate the curvature using energy estimates. Energy. Because since they are glorified Maxwell equations, you know that for Maxwell equations we have energy estimates and so on. So you can do something very similar here. It's a bit more complicated, but it's very, very similar. Once you have the curvature, then you can analyze the gammas by thinking of this as transport equations where the curvature is already given to you, right? And then somehow these other things here are viewed as relations. I mean, the true hyperbolic character is included in here. This, of course, it follows. So the equations here follow from these ones, but somehow these are typically used in combinations with this one in order to get all sorts of relations.
Particular solutions, these Kerr solutions, they are obtained at the level of the curvature, or where could you...
So I'm going to say something right now. Okay, so this was just preparation for exactly for this. All right, so why are these important? You can see it immediately when you talk about, so these are the null structure equations that I mentioned. You can see immediately when you apply all this to Kerr, because in Kerr, it turns out, so one remarkable fact about Kerr is that there exists a principal null frame. In other words, E3, E4, which you can write down explicitly in terms of coordinates. They exist. And such that all curvature components, these are alpha, beta, beta bar, alpha bar, all these curvature components are zero, they vanish in that frame, and only the so-called rho and I rho star survive, right? So these are these sorts of things. There is this RE4, E3, E4, and there is another one which is just like that, but let me not get into these details, okay? I just want to give you some kind of idea. So the very important thing is that this principal null frame diagonalizes the curvature of the Kerr metric. Otherwise, it will be incredibly complicated. I mean, the Kerr, you know, anybody who has worked a little bit with Kerr, you see that if you write it in coordinates, you have a never-ending series of calculations that leads to nowhere. Okay? So it's very, very important to have a conceptual understanding of Kerr. Right, anyway, so this is a principal null frame is essential. In Schwarzschild, in addition, of course, you have connection coefficients. Some connection coefficients are also zero. Never mind exactly which ones, but some are also zero, which is very important. In Schwarzschild, in addition, you have that rho star, right? So you have that rho star there. Rho star will be actually zero in Schwarzschild. And also further connection coefficients are also going to be zero. So many things are zero. In fact, the only non-vanishing components of gamma will be, well, whatever. I mean, I don't necessarily want to write down now again what they are, but there are fewer and fewer. Of course, if you are in Minkowski space, in addition, you also have that rho is zero, and then these ones are zero, these two, and you are left just with these two, which are just geometric. These are just 2 over r in terms of polar coordinates. So these are very simple to calculate. Okay, so that's kind of the story. And as you see, these frames are very important. Now, okay, so now you want to think about perturbations of Kerr. So how you are going to think about perturbation of Kerr? Of course, you can try again to look at the level of the metric, but that's a mess. You don't get anywhere, right? So this is infinitely better. You imagine now a space-time, a general space-time, which is a solution of the Einstein equations, where you have a frame which is close to a principal null frame. So in other words, you have a null frame E3, E4, E1, E2, such that all connection coefficients and the curvature components that you have here, they are all O of epsilon relative to a small parameter epsilon that you have in the problem, right? So this will be O of epsilon. And also the part of the curvature which is not zero in Kerr, you want to say that it deviates very little from the position of the old Kerr. So this will be this O of epsilon here, right? And then, of course, you linearized. You linearize the equations that we had before, right? Exactly these kind of equations. You linearize by saying, well, gamma is going to be gamma Kerr plus a gamma tilde, where all gamma tilde is O for the epsilon. R is R Kerr, exactly the curvature of Kerr, plus something which is O of epsilon. And of course, you get a system of equations now at the linearized level, which looks like this, right? So these are the linear quantities. And you see, it's very complicated to a large extent because of the presence of these things, because this is a coupling. This leads to a coupling which is very, very hard to understand. In Minkowski space, this will be essentially all zeros, and that's why the stability of Minkowski space could be done, right? It's much simpler. But in this case, it's far more complicated, right? So let me tell you a little bit of what we still know. Now, one important thing is that, you see, in this definition, you can say, well, but this frame is arbitrary. I mean, which frame I'm talking about, right? It's an arbitrary frame which is good up to order epsilon. Well, one thing that you can try to do is to see how to change, if you want to go from one frame to another frame by a frame transformation. And here in this story, everything which is O of epsilon squared is good, because O of epsilon squared terms are the terms that we love, right? We like in nonlinear equations. Well, of course, they are still very complicated, obviously, but at least you seem to be reducing the problem to something that you have some control on, right? So the quadratic terms I will neglect, and then look at only terms like this. These are all O of epsilon. All right, so this is very simple. I mean, you just write down what the general transformation which preserves the null frame. So I want to go from one null frame to another null frame, right? Now, so here is a remarkable fact, which I think plays a fundamental role in everything that is done with linearized gravity, is that the extreme null components, alpha, alpha bar. So remember, alpha, alpha bar were, for example, was this one. This was alpha. And if I interchange E4 with E3, I'll get the so-called alpha bar. So these components are invariant up to O of epsilon squared terms with respect to this kind of transformations, right? So in other words, they somehow don't care about the gauge I pick, right? They are okay no matter what I do, right? So this is very important, because this is something that I have to start with, otherwise I have no idea what to do. All other linear curvature components of the curvature, so all other components of the curvature are not invariant, so that's also important. And now, based on these observations of Teokolsky was able to show in 1973 that these curvature components which are invariant actually verify decoupled but non-conservative linear wave equations. Okay? So in other words, there will be some linear wave equations with low order terms which are non-conservative. They are not Lagrangian, they are not conservative. All right. Now, however, they were extremely excited. Physicists were very excited. They immediately declared victory. Teokolsky, maybe other people were more reasonable, but you read a lot in the physical literature that somehow this solves the problem of stability completely. I mean, even though this is just at the level of linear stability, right? Well, actually, Whiting proved something using this. Proved that the Teokolsky equations, so these wave equations which are not conservative, have no exponentially growing modes. Right? Yes.
So you mentioned that the location of the black hole is also
right. So this has to do with the frame, for example, the change of frame.
Is this reflected in any way in these analyses, or how do I see it?
Well, I mean, the whole point is that these are invariant. There are certain components of the curvature. This is quite the remarkable fact. There are components of the curvature which do not depend on this fact. Otherwise, you wouldn't be able to do anything at this level. Anyway, so using this, Whiting was able to show that in the linearized gravity equation is exactly what I wrote earlier. There are no exponentially growing modes, right? So and then in principle, one can show now using gauges that all other curvature and connection components can be controlled once you have this. I mean, once you have control of alpha bar, which are this one, then in principle you can control all the other components, though even this is highly non-trivial. But the question is, does this solve the problem? And of course, we all know the answer. If lack of exponentially growing modes for the linearized equations was enough to deduce nonlinear stability, then the presence of shock waves, extreme sensitivity to data, and turbulence in fluids will be ruled out, because in all those cases, we have more than there are no exponentially growing modes. You can show that there are no growing modes at all in linear theory, and yet, well, you know. So obviously this doesn't solve anything, but of course it was a very important circle of observations and ideas. Anyway, so what are the main results we know on stability? Of course, we know the global stability of Minkowski space. and here I should say that what was important was maybe not so much just the result, but the fact that it uses geometric methods which turn out to be important in many other problems. In particular, it's also important in this problem. The classical vector field method, non-trivial use of characteristics. The non-trivial use of characteristics is fundamentally important. So in other words, you use foliations based by null characteristics. Generalized null condition, which also played an important role, I mean a fundamental role actually, and some kind of very complicated bootstrap argument, which of course by now we all know we can do it in many difficult problems. All right, so now of course the mode stability of the Kerr family, which I mentioned. Poor man's stability, so this is a stability that I mentioned earlier, that if you fix a Kerr solution and you look at the wave equation, just a standard wave equation on the Kerr solution, then you can show sufficient information about the solutions which are consistent with what you might need in the nonlinear problem. Of course, the nonlinear problem is much more difficult because you don't even know the linear equations, but this is extremely important, at least to study the standard wave equation. If you don't understand the standard wave equation, you don't understand anything. And so this was enormously important. All these techniques which were developed by these people were very important. There was a new vector field method which developed as a consequence of this, which is not just based on symmetry, but it's based on many other geometric features of black holes. For example, the horizon, there is a redshift at the horizon. There is something that has to do with the ergo region, the degeneracy of the ergo region. There is something that has to do with the trapping, which I told you the trapping means that you have these null geodesics which sit in and lead to all sorts of technical difficulties. A far region, which has to do with something that, in a sense, you can say was already understood in the stability of Minkowski space. Anyway, more. How much time do I have?
8 minutes.
8 minutes, okay. So, right.
Let's make it 15. Is okay?
15 minutes. It's very generous. Very generous. Great. So, so what are the results we know? There is a scattering construction of the dynamical black holes by Dafermas, Holzegel, and Rodniansky, which means that you solve the problem from infinity rather than from initial data. This is turns out to be much easier, but still quite remarkable that it was done. Then there is a result of Ionescu and myself, which I call, in the Axilly symmetric case, so I'll mention Axilly symmetry in a second, which is based on some partial linearization. So you don't solve the full problem, but you solve something which is still nonlinear. So in a sense, it's a better approximation than just a wave equation on the Kerr solution. It's something which is maybe more relevant. Then there is a remarkable result of Dafermas, Holzegel, and Rodniansky, which has just appeared at the beginning of the year, which is linear stability near Schwarzschild. And finally, work in progress of Seftel and myself on the nonlinear stability of Schwarzschild, but nonlinear. I mean, we are trying our luck with a full nonlinear stability for Axilly symmetric polarized perturbations. So this is actually, in terms of linear stability, of course, linear stability also plays a role here, but the linear stability in our case will be sort of a subset of this. But we are trying our luck with a full nonlinear problem. Now, Dafermas, Holzegel, and Rodniansky, so I think the central point of their approach, which is the result I just mentioned, is a remarkable discovery of a new tensor, which is an S tangent 2 tensor, at the level of two derivatives of curvature. So remember, alpha, alpha bar are just components of the curvature, and they come in the Teokolsky equation. So here you take something which involves two derivatives of curvature, which turns out to actually verify a conservative equation. In other words, it's an equation which has just a wave equation in Schwarzschild applied to this P plus a potential times C, and this potential has good properties. in some sense. It's called the Regge-Wheeler potential, and it's good. So this has actually good energy estimates and more of it, and so on and so forth. So you can start applying all the technology developed in the last 15 years, to which I alluded before, in order to control the decay properties, boundedness and decay properties of this P. Once you have that, then you have to reconstruct all the other quantities. I mean, P, of course, is just at the level of two derivatives of one component of a curvature. So you have to go back and go down and get all the other quantities, in particular those quantities which are gauge dependent, and therefore you have to make gauge choices, right? And of course, that's a highly non-trivial part. In fact, remarkably, this sort of thing they refer to a computation of Chandrasekhar, and remarkably, they don't even prove this, right? Which to me, it's like the most important thing. They say it's just a calculation, but then the rest of the paper is about 170 pages just to do this stuff. So it's a very complicated thing. Anyway, now I said I want to talk about axial symmetries. I want to simplify. So the problem in axial symmetry turns out to be a lot simpler. And let me explain why. So axial symmetry means that you assume that the metrics you are looking at, which are perturbations of Kerr or Schwarzschild, have an additional symmetry which corresponds to a Killing vector field Z. Of course, Kerr itself has that symmetry, right? So it's totally consistent. So it turns out that using this Z, you can construct the so-called enhanced potential, which is a complex scalar. So it's x plus iy, where x is just g of zz, so it's just something simple to calculate. And it turns out that phi verifies a wave equation. So in fact, it's actually a nonlinear wave equation. In fact, for people who recognize immediately that it's a wave map with values in hyperbolic space. Okay? Right? So this is part of the symmetry reduction. Then it turns out that you can work a little bit harder and do a decomposition also of the metric. So the metric decomposes itself into a 2+1 metric and a scalar, this complex scalar. And now you have again the wave map, which is this one. But now, of course, you have to relate the wave map also to the curvature. So you have that the Ricci part of this 2+1 metric, which is here, is tied to this wave map through this relation. And for people, I should say, for people who love wave maps, of course, they usually do wave maps in Minkowski space. And there are lots of beautiful results which were proved in recent years. This would be a great challenge to apply their methods to the wave map, the true wave map, which is coupled actually with a metric, right? So this is a quasi-linear system. It's much more complicated. Anyway, but I'm interested in something else here. Okay, so this is a wave map. Now, here are two problems that I've been working on in recent years. So one is probably what I call modern problem number one. What you do, again, I cannot do the stability in general. It's still immensely complicated in this case. But you can try to simplify things a little bit by keeping the phi to satisfy this equation and simplifying the metric to be the Kerr metric. So you take G to be the Kerr metric. Right? So then you see you get now a system. The G is actually fixed, and you have the Ernst potential of Kerr itself, which exists. Kerr itself has an Ernst potential corresponding to the vector field Z, the axial symmetry. And you look now for solutions of this equation. So this is the equation written in components for phi. This is how it looks around the solution that you already know that you have, which is exactly the one of the Ernst potential of the Kerr metric. So in other words, you have this system of nonlinear wave maps, but you have a solution, a specific solution. When you take x to be A and y to be B, you get a specific solution, and now you want to perturb around it. So that's model problem number one. Model problem number two is that you assume, in addition, you assume polarization. So if you go back to what we have here, I'm going to assume that y is equal to 0, and it's easy to see that this system is consistent. In other words, y equal to 0 is a true solution. So if I start up with y equals 0, it would stay y equal to 0. So this is actually when you do axial symmetry polarization, you really, it's an honest result because you actually solve the true Einstein equations, right? Okay, so the problem now becomes when y is equal to 0, so this simplifies a lot. So the wave equation, instead of being a couplet system, is now just one wave equation, which is dimension of phi is di phi, di phi. This actually you can solve explicitly, right, by exponentiating, and you get just a solution of the standard wave equation. And of course, you tie it to the Ricci curvature of this spacetime metric. So remember, this is a 2+1 metric. You tie it by this. So this is a system that you have to solve, right? These two equations. And it's easy to see that in this context, the final state has to be Schwarzschild. So it's really a problem of the stability of Schwarzschild solution in axially symmetric polarized case, right? All right. So so the conjecture number 1, which is model problem number 1, the stationary wave map is stable under general axially symmetric perturbations. So again, given small initial data, close to the L's potential of Kerr, on a space-like hypersurface, there exists a global solution such that phi is equal to phi 0 and phi converges to phi 0. Now, unfortunately, I don't have time to talk about this. I just want to say that on this, we have made a lot of progress. We proved all the important linear stability results with Ionescu. So this is, the conjecture is certainly consistent at the linear level. And my student, John Stogin, is now doing the full nonlinear result, right? So this is something that I think we understand. So let me go to, I won't have time to talk about this. There are some interesting things about that, but I won't have time. So let me go back to modern problem number 2, which is work in progress with Jeremy Seftel. So this is a system that you want to run. So you are looking for metrics of this form. So phi, this derivative with respect to phi, it's exactly the Killing vector field. So x is independent of phi, and the metric g is independent of phi, right? And you have this nice reduction. And the equations really look like this. So these are the 2+1 dimensional equations. Now, in principle, you could think that this equation is so simple. I mean, there should be no problem to solve this, which is what we thought, but it turned out to be totally wrong. I mean, there's nothing you can do with this equation. If you try to linearize, you get a mess, and you never get anywhere. So, so we really had to go back to the standard picture using curvature and connection and so on and so forth, which is what we did. All right. So again, we introduce a frame very similar to before. It was a null frame E3 for E theta. But now, just in the, because of the reduced picture, you can do this just in the 2+1 picture, which things simplify. So a lot of these components of connection and curvature are simpler. In particular, they are all scalars now. So this is a scalar, this is a scalar. And anyway, I don't want to bore you with all these things. They still are sort of, this frame that you can write down. These are the equations written in full details, but I don't. I mean, I don't want to scare you. They are not that complicated, actually. It takes just a little bit to get adjusted. But in any case, I want to go back to this business of Teokolsky equation. So there are these Teokolsky equations, which now are scalars. So in my case, alpha alpha bar are scalars. And these are the equations that actually they satisfy. Alpha alpha bar, again, just like in the general case, they will be invariant up to of epsilon squared. So there are two invariants of the problem up to terms of order of epsilon squared. And they verify this kind of equation. So this is the standard wave equation. Actually, you can take now the metric to be the Schwarzschild metric, in fact. So this you can think of being Schwarzschild. And these are some derivatives of alpha bar, and similarly here. And you can very easily see that this equation is not conservative. So there is not much you can do at this level. So, so the idea is to find a quantity, to find a good quantity, which linearizes the only component of the curvature, which is, say, the one which is close to rho Kerr, is non-trivial. And I cannot, I mean, saying that it's close to rho Kerr is kind of misleading because rho Kerr, only in a system of coordinates, I can talk about the true value of rho and Kerr. But I don't have a system of coordinates to start with. So I cannot even talk about this, right? So the issue is how to linearize without doing this, how to find a quantity which is invariant and which is tied to rho and which is small, which is 0 in Schwarzschild, right? So this was sort of major thing for us. So we found that there is such a quantity, which is at the level of it's the level of this x, which was e to the 2 phi in the previous slide. You see, it's just derivatives. So this is clearly a covariant expression. It's a tensorial expression. Minus this rho, which is the one that you want to linearize, minus this. This quantity tends to be 0 in Schwarzschild, tends to be an invariant of order of epsilon squared, right? And it satisfies a good wave, I mean, not a good wave equation, unfortunately, actually, but one which is still a wave equation, which looks like this. And it's unfortunately, it's still tied to the Teokovsky quantities, alpha, alpha bar. So we're hoping to get something which doesn't have anything on the right-hand side. It will be just O of epsilon squared. But it turns out to be much more complicated. However, there were some very simple relations that are satisfied between this p frag, this quantity which we have introduced, and alpha bar, which are some kind of simple ODEs like this. And inspired by the fact that we knew that Fermat's, Holzhegel, and Rodniansky already had a good quantity, which was at the level of the second derivative. I'll finish right now. Which was at the level of second derivatives. We realized that what we had to do is just to differentiate this with respect to E3, then differentiate with respect to E4, commute to this, get rid of these terms because of these relations, and you get finally a wave equation which looks very simple, and it verifies, obviously it's a wave equation with a potential. The potential is very nice. It has good energy estimates, and therefore you can do more of it, and you can do all sorts of things. And once you have that, then you have to work a little bit harder and get the full story. But unfortunately, given the time, I'll have to stop. So I'll stop here.
Thank you.
Here. Let's get to see it.
Comments? No questions? Yes?
I have a question about this final state conjecture.
Yes.
Did you say that Kerr is a unique end state?
No, I didn't say. I said that I want to prove that it's unique.
No, I'm the conjecture. So
Sorry?
the conjecture is that the single Kerr black hole is the end state.
No, wait. This is different. I mean, we're talking about different things. So one is whether there are any other stationary states besides Kerr. That's a rigidity conjecture, right? And so far, we don't know. I mean, we have only partial
I
results.
was thinking, suppose you take initial data which have the form of two approximate Kerr black holes far apart, and you give them velocities in opposite directions.
You have to ask Thibault about this. I mean, I really, we are unfortunately, we are still very far from that kind of results, unfortunately. Right. So we are really at the one-body problem. I mean, from mathematical theory of GR is just at the level of the one-body problem at this stage. The two-body problem is something that maybe if we go to Tuesday talk, maybe we'll learn. I mean, I think it would be very, very nice if we start getting into the two-body problem also. But so far, no, I haven't seen any serious attempt to do that in the mathematics.
So, any more questions or comments?
Of course, needless to say, this experiment, this recent remarkable experiment at LIGO, is based. It preassumes, based on, of course, on numerical experiments, it preassumes that the two-body problem is stable. Therefore, in particular, the one-body problem is also stable. So the stability is not under question from a physical point of view at this stage. But we don't have any serious mathematical results at this point.
Okay, so let's thank the speaker again.